Hello and welcome to this Fluree developer video. My name is Andrew Johnson. I'm a software engineer at Fluree. And today we're going to be walking through a demo of Fluree's value in the use case of verifying university credentials. If this is your first introduction to Fluree, very briefly, Fluree is a data management solutions platform that leverages blockchain technology to produce graph relational databases that are also Web3 compliant and built for a semantic web. I know that's a lot of jargon, but hopefully that'll make a little more sense as you join us for this video today. This video is also part of a larger series on credentials and identity management. If you'd like to see more about that, you can go to our website, www.fleur.ee/credentials. The credentials subdomain specifically here is going to talk a lot about how Fluree can be leveraged not only in the context of this specific case of university credentials and transcript verification, but also in general identity management more largely. So again, if you're interested in any of that outside of this video, please visit our website /credentials to learn some more. We'll go ahead and jump right in, and I'll explain a little bit of the context for this particular example. Today we're going to be demoing an app that I've built to show off some of the ways that Fluree adds a really unique value proposition to those in the world of credentials management, specifically in the world of university credentials, at least for the context of this app. So we'll jump into the use case discussion here. Hopefully we'll get a sort of a better sense of what we're going to be doing today and some of the things that we'll see that are pretty neat, that really Fluree uniquely offers that other databases and database management solutions can't quite do. So in the world of verifying university transcripts, there's a few sort of use case scenarios that we have to think very specifically about. So this app specifically will be looking at how we can verify that the transcript that an applicant for a job or for a sort of recruitment network, that document is verifiably true, but also does so in a way that helps avoid a lot of the really sort of expensive solutions in the market today, and really leverages some of the forward-facing technology that we at Fluree have been trying to build into data solutions. So when we're talking about the use case of a technology like this in a market like this, I'm thinking specifically about university transcripts. We first have to think about access. So to some extent, a university wants to publicly, or at least semi-publicly, make available their database so that third-party organizations like employers or recruitment agencies would be able to verify transcript credentials. And we'll think a little bit more about that. What are the problems that go into that? What is the extent of access that we want to make available? So that's one thing to think about as we start to move forward here. The second is going to be privacy. We need to expose sufficient data to verify that transcript without, of course, exposing anything confidential or identifying about a student that would be, break regulations for sort of federal education law, or that would just generally open up either the university or students to a loss of privacy and access to private data. And third, we need to think about security in a larger sense. So, of course, a big issue with credentials in general, especially things like transcripts and certificates, is the possibility that they could be tampered with, that someone could spoof that data, that they could provide a forgery of that data, or similarly, that someone who has access to that data could use it maliciously. Someone who should be a sort of within a trusted domain could have access to transactions, deletions, updates that we wouldn't want them to have access to. So we'll be thinking about all three of these things moving forward and thinking about some of the problems they pose, but also some of the ways that they're very natively, very easily handled by Fluree. So let's dive into the obstacles we brought up in that use case a little further. So the first obstacle we'll look at here is going to be this sort of this competition between, on the one hand, wanting to think about public access versus, on the other hand, wanting to think about the privacy of data that we're trying to protect. So how do we build a publicly or semi-publicly accessible database for external users to validate university transcripts without exposing private student data? A quick hint here as we get moving forward, a lot of the answers to this question are answers to the same questions being asked in the blockchain space. So if you're familiar with Bitcoin or Ethereum, blockchain more largely via Hyperledger, etc., you might have some of these questions in mind already when you're thinking about this tech stack. But as a quick point, we're thinking of them not as they relate to something like a cryptocurrency, but as they relate to a database where we need to very, very quickly query data, we need to transact data, and we need to think about who has access to this sorts of database information. Cryptocurrencies that are already thinking about public access for private data are not thinking about them in terms of being able to easily, quickly, affordably share all these things. And these cryptocurrency blockchains, of course, aren't built for database solutions in mind. So a quick hint there, a quick teaser for what we're going to see moving forward. But let's move on to the second obstacle we have here. So data tampering, in the world of transcripts in particular, how do we protect against even microscopic or expert attempts at document forgery? It's a big issue, and it's a reason why universities go to great lengths to both secure the sort of digital assets of a student's transcript, but also to make sure that if a student needs to get their transcript to an employer, that there are extreme steps, very costly steps that they go to make sure that this data tampering can't take place. The third one is malicious intent. So how do we plan for and handle a scenario where a trusted user with transaction authority submits malicious transactions into the database? So imagine, for instance, an administrator who updates a student record with a tampered transcript. If somehow, for some reason, and we don't like to think of these edge cases, but they're of course the most important, perhaps. We don't want to, if a student paid an administrator to upload a fake transcript that presents them in a false but more valuable light, how do we protect against that if the administrator has a transaction or update access? Similarly, an administrator who deletes a student record altogether or removes valid transcript data from that record. We'll think a little more closely about the difference between these two, what they look like in terms of data. But they're worth coming back to. So on the one hand, we have a certificate, or we have a record in the database where we are uploading a different document, but the record stands and we might be approached by a student who has that forged document. In the second situation, we have a record in the database where the certificate has been removed entirely, or it's been replaced by some value that will not help the student out at all. They're slightly different use cases, but they're really interesting to think about, and we'll look at them a little more closely in this demo. The next question are, what are solutions out there? Of course, this video isn't the first time these issues have been thought about, and so it's not the first time that we've had to invent solutions to these. So one could say, for instance, these problems have been solved, and the way that they're solved today is by combining legacy database technology with third-party security software. So universities are paying extraordinary amounts to have their database data guarded by things like firewalls or by logging software that can guarantee the validity of the data that's being presented. Of course, this is incredibly important for universities, incredibly important really for any sort of certificate authority, whether that's AWS certificate management, whether that's hospital records, et cetera, et cetera. So we're drilling into a specific use case, but these questions are valuable in a larger market. The second point here, though, is that in the current setup, where again we're combining legacy data with third-party security software, end users, the everyday user who's relying on these current solutions, are still having to put their trust in good faith stewardship of security reports. So both, you have to assume that the security software built is doing what it says it does. Second, you have to assume that when security errors are coming up, that those are being shared with the public. And third, that this sort of whole general system of university, for instance, relying on the security software and working with third-party organizations like employers, like students, like recruitment agencies, that all of that is happening fully in good faith. So we don't have a way, essentially, for the data to defend itself or protect itself. We don't have a way for the database solution itself to build in the security to its own structure, to the own sort of DNA of itself. And that's something that we're going to look at going forward. And before I leave the slide, this is an incredible, the reason this market is so interesting is because universities pay incredible amounts of money for the security and for the sort of constant work that goes into this additional layer of protection on top of their data. So where does Fluree come in? What does Fluree offer? How are we different in this market? So as a graph database built on blockchain, that's a really important part here. First of all, our data is natively immutable. As anyone who knows about blockchain knows, when you delete data or update data, you are adding an assertion of a new state of data to the blockchain. So as a new block goes in with new data about a particular record, the old data about that particular record is never lost. And in fact, in order to prove that the current instance of data is still valid, we essentially have a sort of chain of validity, where at any point, if any of the data in that chain breaks and there's sort of a situation where data has been tampered with, the whole structure it doesn't validate itself. It's always self-validating, and all the data is always immutable, so that any new deletion doesn't replace, in a historical sense, the previous data that was existed for that record. We'll look a little bit more what that would look like in this use case once we get into the actual app that we'll be demoing today. So, in being immutable, we also have, again, a traceable history of all additions, updates, and deletions. Of course, when you're looking at just the current instance of the database, that might not be clear. But in any situation where we have to dig in and do a sort of native audit, there's no need to bring in third-party software. There's no need to actually build a sort of logging platform around your data. The data just natively does this. It is the structure that the data exists in. And finally, it's built on public-private key cryptography, so that every single database interaction can be both natively permissioned and traced to the public user who issued it. Now, there's a lot to be said here, and our other videos explore all the sort of permissions and authorities in more detail, so I encourage you to look at those. But it's worth mentioning that this is one way that we can begin to think of a public or semi-public distributed ledger system, where there are several people who are authorized to transact, several more people who are authorized to query, and yet we can still have sort of native permissioning and native traceability to the users who are transacting what. So that's going to be very important moving forward. We're also going to lean in a bit on this cryptography because encrypted hashes, so fingerprints essentially of data, are both very important in blockchain, but they can be very important here too, in this particular use case, for verifying the validity and the specificity of the data we're looking at. So we'll come back to that. So lots of intro, lots of sort of summary of this use case and of the sort of data concerns going in, but the fun part here is going to be us looking at this demo. So I'll explain a bit what this demo is going to be, but essentially there's three main things we're doing here, and they're all really interesting. One, we're going to go ahead and verify digital transcripts. We're going to set up a sort of use case where all of this is happening. We're going to verify digital documents by querying a SHA-256 encrypted hash against a public-facing database. It might sound a little confusing. It'll be very clear when we move into the demo. But essentially, we're going to use an encrypted hash of a transcript to keep from any public details of a transcript being publicly available, but also we're going to get from that an essentially unspoofable, non-reproducible fingerprint of a very specific document, and we'll be able to essentially be given that same document, that digital document, by an applicant where we will be able to very easily, with public technology, make at the time of validation, make a hash of the document we've been given. And those two hashes can only match up with statistical certainty. They can only match up if they are the exact same digital document. We'll look a little bit more at what that looks like in the app. The second thing we're going to do is we're going to show off how we can leverage Fluree's graph relational data references and the way that you would use and reference a normal graph DB. But we're going to do so with some more interesting things because of being backed by blockchain. We're going to be able to do so in a way where we can still sort of time traverse across history. So if there's any issue, and this is going to be very important for these sort of malicious intention use case scenarios we've talked about, if it's important to see the history of data, to see the history of transactions to a particular record, or the history of transactions that relate to a particular document, we can do both of those things in a way that no other database on the market right now can. And third, we're going to demonstrate how this blockchain data is the thing that drives these particular native audits against these maliciously intended transactions. All right, so that should do it for all the talking. We're going to look now at the actual running of this demo, and I'll go ahead and introduce both the code of this. This is sort of made to appeal to developers, but hopefully if you have no sense of sort of basic front-end development, you'll still be able to appreciate the value of this as we go into the sort of user interface and user experience of the app as well. So if you are following along with the with the repository of code that we provided alongside this video, you'll see that on initially opening it, you have just a very basic and empty table. To go ahead and run this, it's very simple. And we'll do this in a second after I dive into the code. You'll just need to go into the repo and start up a Fluree instance. So essentially, you'll run the script to start a Fluree database instance. And then when you refresh this app, at the top level, it should run a script to go ahead and transact the schema, the basic seed data, and the transactions that you'll need to really just start playing around with this app. That should all happen for you. Really quickly, I want to dive into the code to explain a little bit about what goes on when you're bootstrapping a database instance in general with Fluree, but specifically what sort of data we're going to be working with here and what sort of data organization we're going to have from the schema. So again, if you're not super familiar with Fluree in general, or more broadly the schemas that operate within graph relational databases, I encourage you to look at some of our other videos or our documentation. We're not going to go into total detail here, but I do want to sketch out how the use case we've just described, this sort of this validation of university transcripts, is going to be represented by the schema that we have in front of us. So the very first transaction that we'll do, besides the sort of the bootstrapping transaction that a Fluree database does as it's starting up, when it's setting up its basic system collections, etc. The first block besides that, though, is going to be this transaction where we go ahead and set up this initial schema that's going to set up the entire structure that will manage both our queries and our transactions moving forward. So you'll see here that we have 4 collections. It's very, very simple, this particular database. So we'll have a university collection, a certificate collection, a verification org collection, and a user collection. Really, the idea here is that universities will be able to upload certificates. The certificates will be scrubbed of any private data. In fact, the records really will just show a few things. We can dive into that here. Most importantly, they'll have an encrypted hash. It's a SHA-256 hash of the transcript PDF for that particular student. So if you're not familiar with SHA-256 hashes or SHA-2 hashes, hash functions in general, SHA-2 or SHA-256 is a hashing function that produces a sort of cryptographic fingerprint, specifically in a 256-bit map. And a few things to be said about this. We don't have to dive into cryptography here, but first of all, this is not a Fluree proprietary sort of thing. This was developed by the NSA. Very importantly, when we talk about hashes, we often hear the word fingerprint. The idea here is that we can take a PDF document, which is essentially a very long string of characters, and we can take that PDF document and run it through this function. What we get is a relatively short string of characters that is impossible to reproduce other than by just going ahead and hashing over and over again the exact same document that you had just hashed. So if you take a PDF, run it through a SHA-256 hash, and get an encrypted hash as a result, continuing to run that exact same document through a SHA-256 hash will continue to produce that exact same hash. It is an exact fingerprint of that document. And yet, changing even a single pixel in that document, going in and just literally changing one pixel, or if you had the string of characters that constitute the document, if you changed one of those characters, the hash you got would immediately be extraordinarily different. It would be not just one character different, but in fact, totally incontrovertibly different from the other hash. So the point is, it is impossible to spoof the hashes that we're producing from these SHA-256 functions. And similarly, it is absolutely impossible to take this short encrypted hash fingerprint produced by the SHA-256 hash function. It is absolutely impossible to take that and reproduce the document from it. So it does 2 things. It, 1, protects all the data that was run through that hash function. So it protects the data that is on that transcript from public access. It also makes it absolutely impossible to take any other document and produce the same fingerprint. It also makes it absolutely impossible to take the same document, change just a few pixels, like a GPA average, for instance, and we'll take a look at that in a second, and produce the same fingerprint. So we have a bunch of certificates that'll be uploaded where it's just the hash, the university that uploaded it, and the date of being uploaded. So again, although it is statistically impossible for any of this to be replicated or spoofed, if in the almost impossible scenario where 2 hashes are identical, you would at least be able to tell based on the date of their going up. If you see that there are 2 matches for the same hash, again, statistically impossible, but if you see that there are 2 hashes that match the document that you're trying to verify, you could almost certainly tell which one was the one you were looking at or needing to look at based on the date instant when they were issued. So moving past that, we will just very simply have a university with a name that will be associated with these. And I should mention that as well. If there's another certificate that matches by the hash, again, statistically impossible, you would also be able to say if it came from a different university than, for instance, the document suggested. We just have some very basic ways that make this even more robustly secure to make sure that this would never, there would never be any way to spoof or to accidentally have the same record twice. Finally, we have these verification orgs, and so we're gonna look at the UI that maybe a verification org would see. So whether that's a recruiter or an employer, the idea is they have applicants coming in. Here are the references to those applicants. They have applicants coming in, presenting them with these digital documents that they've received, these transcripts they've received from their university. We'll look at a few cases where people are acting in good faith and hand over the exact document that they got from the university, and we'll see how this works out perfectly to verify it. And then we'll look at a few cases where these applicants are coming in, a verification org is running the documents they give, and some fishy things happen. And we'll take a look at how, again, Fluree is able to natively audit those fishy things without the addition of any sort of software, any sort of logging ability, just by using the basic structure of the data that we have here. Okay, so we'll really quickly, we'll look at some of the seed data that's going in here. Again, it's gonna just correspond to the schema that we set up. So we're gonna have universities, we're gonna have certificate hashes, and this is an example of, for instance, that output from the SHA-256 hashing function, this unique string of characters that is unspoofable and from which you cannot recreate the document that produced it. Then we'll have some basic users that are gonna correspond to those, and then we're gonna basically just, with this very simple data, it's truly all the seed data that's going in, we're going to be able to verify whether these applicants are providing us with the documents that correspond to the data in the database. Okay, a lot of talking. We should be able to jump right in here. So I'm going to start up a brand new Fluree instance just by running the script that bootstraps that. We'll see that this begins to happen in front of us. Essentially, all that's happening here is the very initial transaction is going through to give the sort of system collections, to bootstrap the system collections that will generate the sort of graph presentational data on top of a blockchain data structure. And if we now hop over to our app and go ahead and refresh it, we will see that after a few seconds, it should just take 2 or 3 seconds. Yes, we get the fully seeded database on top of the schema that we had just built. We can go ahead and test out what this is all going to look like. I think it's pretty fun. So we have 4 applicants here. We have Jane Doe, Kalpana Rao, John Smith, and Yuta Takashi, all of whom are coming to, they've applied to a position, and through our recruiting agency, they've presented us with some digital documents. So we'll look at those PDFs in a second. And we are now running these documents against this public-facing database, a public-facing database that has no personal information about any of these students. And even though it has certificate records, those certificate records don't tell us anything about those students, again, to protect the privacy of student information. And all that we'll be able to do is have our app, again, use this very, this one line of code to run these same documents through the SHA-256 encryption, and then see, is the hash, the unique, unreproducible hash that's produced that we get from running the document through that SHA-256, is that hash associated with a certificate in the database? And if it is, the only way that would happen is because we have been given the exact same digital document that the university gave that student. It is literally impossible to reproduce that hash in any other way. So let's look at a good faith user participating in a system that hasn't been tampered with at all, running exactly the way this is supposed to run. So we have Jane Doe here. We have the J Doe transcript that she provided us. We can take a quick look just to drill in here on some of the details. So basically it's very, very simple, and of course there would be more information here, but we have a transcript for a student, Jane Doe. She had a 4.0 GPA from the University of Virginia, and it was issued on this date. So we have this transcript. We're going to go ahead and upload it. In uploading it, and actually I'll pop open our developer tools right here, I have just a line in here that's logging out the hash that's produced by that. So this hash, in fact, is the SHA-256 hash generated by running that document through the function. And if we verify, all that's happening is there's a quick check to make sure to see if that hash exists on the database and is specifically associated with a certificate record. And in fact, it was. So this is a valid certificate. It was issued by the University of Virginia on June 1st, 2018. Exactly what we hoped for. Everything happened exactly like it should. So we have... Well, let's go and let's look at someone who, the next step maybe is we'll look at someone who is giving us a tampered document. So we have actually a real transcript for this student. So let's say this is the real transcript. This was the one issued by the university. So University of Virginia, Kalpana Rao, GPA 3.0. Maybe the student wanted to come off like they had a higher GPA than 3.0. So 2 things I want to do. First, if I upload this valid document first, it'll verify this is the one that's gone through. First, I want to point out this is the hash for that document. Notice that it is very different from the hash up here for this document. We'll verify it and it'll be true, valid certificate. But now what if we got a document from a student where the document itself had been tampered? They had tried to forge a document by maybe editing a few pixels or a few characters on that. So the previous certificate we got, the previous transcript we got, they had a 3.0 GPA. What if they submitted one where the only difference was that 0, the 3.0, was now a 3.8? So just one character has changed. And there's a few things I want to point out here. First of all, when we upload this document, look at the fact that even though it was just one pixel that changed, the actual hash is wildly different. So none of these characters really correspond to any of the characters we see down here. And this is what I was trying to show earlier. A SHA-256 hash it produces a fingerprint that is absolutely unique to the document and doesn't correspond at all whatsoever with the structure of the document. So it easily proves that even the slightest of changes to that digital document will produce an entirely different hash. And we also want to see what happens when that student submits a false record. And of course, we get exactly the thing that we want to see. That certificate's invalid because there is no certificate record that has that particular hash associated with it. And we can search just by that hash, and we don't have to rely on any personal information whatsoever. Okay, that's all very fine and good, but here's some really interesting cases. And we talked about this in some of the malicious intentions or malicious edge cases in the PowerPoint just previously. So what if we have a student who has somehow convinced a administrator who works at the university to upload a tampered document? Maybe the original document they had, and we'll take a look at this. Let's say the original document that they had, they didn't do great. Well, actually, he did fine. He had a 3.5. It's a good grade. You shouldn't stress too much about school, kids. But let's say that this same student gets an administrator to instead upload this document. We're calling it suspicious John Smith. So let's take a look at that. I'm saying it's suspicious because it's a 5.5 GPA. Usually that doesn't exist. And in fact, the date is 2020. I'm being a little silly here, but the point is, imagine you had a candidate who came in, said they had a perfect econ degree with a 4.0 from Harvard, and they are failing miserably in the interview. They're doing very, very badly. You have every reason to suspect that they have no basic economics understanding. So let's say that student had gotten an administrator to transact this incorrect certificate and this incorrect transcript and upload it to the certificate record in the database. So in this scenario, something weird is going to happen. It's going to come up as verified, but we have reason to believe that that's not the case. So again, it says it's valid, but as we then go in, and this is an interesting thing. So I built two sorts of queries here. Both of these two queries actually, again, just drill into the native data that exists in Fluree. So the subject history is essentially going to say, okay, this record was verified. It pointed to a certificate record in the database. So there's a subject entry for this. There's a subject entry in the database where the object of this certificate hash has pointed to the hash we provided. And yet we have reason to doubt this data. So show me the history of that entire subject. And what we see is that at block 4 of the database, there was one uploaded hash. And we can even see the auth record that was associated with the transaction, because every transaction is backed by a sort of private key signature where the private key might not be visible, but the public auth record associated with that private key that's derived from that private key, that auth record is visible. And in fact, we can see exactly which user is associated with that auth record. So this first transaction that went through on block 4 was transacted by this one person, but we see that on block 5, a different hash was uploaded to this exact same record. So we're looking at the history of this particular record and predicate and looking at the different objects that have been associated with it. And we see that a different user with a different auth record put up this separate hash. And in fact, so this is the hash of the very suspect transcript. And look, that is the hash that was uploaded by this other user. So we have reason to believe, I've of course named them very insanely here, but we have reason to believe that this auth record might belong to a user who has either maliciously or by accident, but either way, incorrectly uploaded a transcript that shouldn't have gotten uploaded. So that's a very, very interesting thing that, of course, universities can do today, but they have to do it by relying on logging software that is auxiliary to their own system, by paying for sort of third-party protection and building up a variety of defenses and logging to avoid this themselves. Whereas Fluree just does this very natively, and it does it by sort of looking specifically at all the objects that have been associated with a record that we know of. Now, there's one other use case that we talked, another malicious example that we talked about that is really interesting as well. So what if the opposite of this happens? What if a student comes, they have a document that looks valid by all means, they perform very well in the interview, and yet, for some reason, the document comes up as being invalid. So we have this Yuto Takashi, we have this document from them, looks valid, they seem to be valid, and yet when we run it up into the database, we find that the certificate is invalid. So what's happening? We're finding that the hash produced by this document doesn't match any current records in the current state of the database at all. So in a normal database, you really couldn't do much because you can't query, the moment that someone changes the data for a particular subject record, you can't query data that's not there. And in every other database, that data just isn't there. Similarly, a traditional database might have logs that go through and show all the edits that have taken place. But most of these logs don't have the same querying power, the same sort of search, leverageable search engines to sort of query them because they are logs, they are not a database. So there's no easy way in any traditional database to figure out if there's been some sort of malicious use that's gone into producing the scenario. In Fluree, though, we can take this hash, so this recent hash that we just uploaded, the hash that we produced by, the hash that we produced by running that document through a SHA-256 function, we can take that into a very basic query that says, has there ever been, in the history of this database, a subject record that previously pointed to this data? And we do that by going to it. So this is more of an object history than a subject history. We're taking an object, this hash, and we're saying, has there ever been a subject that referenced this object? And when we go in there, we see a very, very similar scenario. So on block 4, there was a subject, there was a certificate that pointed to this particular object, and it was transacted by this particular auth record. And then on block 5, there was a deletion of that, and whether it was replaced by new data or whether that particular subject was made to not point to any object whatsoever, it is besides the point. I mean, we could also query that data. We could find out exactly what that data is. But we can also just see that this particular object record was removed from the subject it was associated with. And why is that? It's because in a blockchain, there's no such thing as a deletion. So if you do what happened here, if you transact a deletion, if you say delete this object from this subject, the deletion itself is actually an assertion of new data. It's an assertion of a new fact. So the fact that the fact that was represented by this bit of data in block 4 was this subject is associated with that object, and that's true. And when we delete that, when we want the current instance of the database to no longer reflect that, it is still an assertion of a fact. In the blockchain metadata, you'll see a piece of metadata that says this subject points to this object, but that fact is no longer true. It is now false. And if it were replaced by a new object, if someone had updated that subject with a new object here, then it would say this old fact is now false and this new fact is now true. That's just how blockchain works. Everyone who understands cryptocurrency knows that, of course, that when you when someone adds bitcoins to their wallet, or rather when someone gives bitcoins to another user, what happens is a simultaneous deletion of bitcoins from their wallet and an addition of bitcoins to another person's wallet, that there have to be those sort of equal and opposite facts. The real value here is that while you do have a graph relational database of the particular current instant, all of that data is driven by blockchain data as well. And so when you have to drill down, like we just did, when you have to drill down into the history of that data, it is just natively there. It proves itself, it audits itself, and the data is structurally immutable, so that either of these use cases, these malicious use cases we've looked at, both of them are entirely protected and made totally transparent within the structure of the data. So we essentially have here a way, and this is just a way to show you that this data all exists. But of course, imagine if all of this data presented itself immediately. If you wanted to sort of generate some sort of user experience or generate some sort of feature in your app so that anytime a transcript was deleted, there was sort of robust, visible information of that happening. There were alerts that went off. There was a dashboard item that that's triggered on all the other admins' availability or on all the other admins' user interfaces. That would be just very, very easy to do because it's very, very easy to get this data. And similarly, we also have a way of tracking exactly who did it. So in this scenario, we have just really two auth records transacting everything. but we immediately have reason to revoke the authority of this particular user because it is impossible to transact into the database. It is impossible to transact into the database without signing that transaction, and in signing it, tracking it to a public auth ID that is associated with your private key. So if you have any access to be able to transact to the database at all, you're able to do so not with public access to your private key, of course, but with public access, public visibility to the auth record that is associated with all of those signatures. So that's quite a bit of information we've gone into here, and I just want to reiterate that really the really neat value here is that we were able to very, very quickly with a very, very simple UI produce an app that could verify the validity of digital documents without having to actually expose all the private data embedded within those documents. We're able to do it in a situation, right now we're just running one local node, but you can imagine if you leverage blockchain sort of distributed ledger potential, this could happen across various nodes, and it wouldn't change anything because you would still have auth records associated with all the people who had transaction access. So you'd be able to trace back any whiff of malicious intent would be immediately traceable. You also have an ability to open up outside of transaction access. So assuming that just university administrators have transaction access, you can give query access, which is all that we've been doing. All that we've been doing throughout the use of this app is query access. You can give query access to either a semi-public network or a fully public network. And those people are able to query all of this without actually being able to learn anything about any of these transcripts that wasn't provided to them by the applicants themselves. So if Jane Doe hadn't given us, Jane Doe's transcript, there would be no data in the database that actually showed anything about this transcript. In fact, this data isn't even there. The only thing that's there is a cryptographic fingerprint of that data. And similarly, we've looked at several really important and really specific malicious cases that in today's university credentials management market, both of those unique and independent malicious cases require an exorbitant amount of effort to secure against them, to log when they might have taken place, to build up firewalls that give very permissioned access. And we've seen how all of those things are just very natively, very simply, and just intrinsically handled by the data structure of Fluree because it's built on a blockchain database, and because that guarantees all of the data that we're able to query through a graph relational structure. So I hope that was helpful. Again, if you're interested in the credential market or identity management in any way and are interested in looking at how Fluree solves a lot of particular use case issues in those, I encourage you to go to our particular site that deals with that market. So not just fluree.e, but fluree.e/credentials. If you have any questions for me, you can reach me at ajohnson@fluree.e, and I hope this has been a valuable video for all of you. Thanks so much.